All right, in this video, we're going to start to talk about centers of gravity using multiple integrals, section 4.8. So the idea is now that we have what a double integral and triple integral is, and we understand kind of how they work loosely, we're going to be trying to figure out how we can find the center of mass of different sorts of objects, both two-dimensional and three-dimensional. Okay? We're going to start by defining some terminology here. So we'll first start by saying, suppose that a lamina, which is really just kind of like you can imagine as some sort of a plate or just some sort of a space. It occupies a region in the XY plane. So maybe again, I can imagine that I just have something that, I don't know, looks like this. This is D, it's a lamina, just some space in the XY plane. And maybe its density in mass per unit area. Again, I'm thinking about this as two-dimensional. Maybe that mass at any given point of this plate is given by a function. Maybe I'll call that function rho of x comma y. So essentially, if you give me an x comma y point in this space, the function rho is going to say, give me that point and I'll spit out the density. All right, so if we think about then how rho can ultimately be defined, like how could I ever really determine something like this in an actual plate? I don't have any sorts of functions in the real world that could tell me like the density of the table in front of me at any given point on the table. But here's what we have for the meaning of that rho of xy. We interpret rho of xy to mean rho of xy is really equal to a limit of delta m over delta a. And I'll define what these different pieces of terminology are as well. Here we'll say that delta m is the mass of the portion of the lamina in a small rectangle containing x comma y. So again, while it might be hard to figure out the mass at a single point, if I imagine putting some sort of a box around this point, I might be able to find the mass there, right? Because like I could actually like cut that portion out, actually like measure its mass. That's not too difficult. I could also then say that delta A is the area of the small rectangle in blue. And so what I'm interested in is taking a look at, according to this limit, what is the mass when I divide by the area? That should get me my density. But of course, I want to do a limit of this. So I want a limit is taken as the dimensions of the rectangle approach 0. So as that rectangle kind of shrinks down further and further and further, I can go ahead and start to think about that I would be starting to be getting closer and closer and closer to the actual density at that point. So then I can say that based upon how this is defined, maybe intuitively, we could say that the mass of the lamina is given by the following. Maybe I could say the mass then could be, well, I really kind of want to go ahead and like add up all the masses across all the different possible points within my region. And I could do that by just imagining that, well, I'm kind of treating this mass as a function of two variables, and if I want to go across all points in D, I could represent that as a double integral. You'll notice this is almost exactly the same formulation as what we did when we built a double integral. We had a function that we were interested in working with that took in points x comma y and spat out a result. And we were interested in moving across all points in the region. And we did that by chopping up the region into little kind of square rectangular pieces. So this is at least the idea of what we have here for computing mass. And with that idea in mind, we can actually define what we call the center of mass. So the coordinates here, x bar comma y bar, will stand for what the center of mass is for the lamina. I can kind of imagine the center of mass of a 2D sort of a figure like this as kind of being like the balancing point. As in, like, if I was to hold this up as a piece of paper, like where on it would I want to put my finger? So if I held this perfectly flat, I could balance it on the tip of my finger. Okay, well, obviously this point here might not be the best point to try to go ahead and use, unless, of course, the region was very dense over here and maybe not as dense over there. So density definitely plays a factor. So when I find the center of mass, I have these coordinates, x bar comma y bar. And as long as I have a density function given by this rho, these would be formulas that would allow me to compute the center of mass. I can see that if I know 1 over the mass, I can multiply it by the double integral of x times my density. And if I want the y coordinate for the center of mass, I do 1 over mass times the double integral of y times the density function. As I state down here, 3 double integrals would be required to find the center of mass are actually required here, because I have to kind of do 1 double integral for each x bar and y bar, but then also for the mass itself. Okay. So as I state down here, we can view double integrals for each coordinate of the center of mass as like weighted averages. That's what I'm trying to consider here. If some spots are a little bit heavier than others, I want kind of a weighted average. And sometimes you'll see these integrals up here go by different names. You might have heard these possibly if you've taken a physics class before, that sometimes we refer to these as moments of a lamina about an x-axis or about a y-axis. All right, in the next video, we'll take a look at how we can actually find the center of mass for a specific region, and we'll actually do some integral calculations.